Welcome to the first lecture on Introduction to Computer Architecture. My name is Simon Moore, and today I'm going to tell you about technology trends and design challenges, and also give you a general overview of the course. This course comprises 16 lectures. The first 10 are on processor design, and the remaining 6 are on system-on-chip design. The last 6 lectures in previous years were taught by my colleague Timothy Jones, but this year I will be lecturing those as well. So let's give you a quick overview. We'll begin by looking at technology trends and design challenges that motivate how we design processors. Then we'll look at digital system design, which links in very closely with the ECAD and architecture labs. And in the labs, you will be using a RISC-V core that we've designed in-house. We'll then explore 8 great ideas in computer architecture that really sort of form the foundation of how we design processors. And then we'll look at reduced instruction set computers, RISC, which is a very common design philosophy for processors. We'll then explore executable and synthesizable models. In other words, how do we actually design processors, how do we simulate them, and so on. Then we'll look in more detail at pipelining. So we'll spend 2 lectures exploring how do we build pipelined processors. In other words, how do we try and execute more than or how do we process or work on more than one instruction at a time in order to get improved performance. We'll then explore memory hierarchy, so things like caching, and then look at what hardware we need to support operating systems. And then in lecture 10 we'll explore alternatives to RISC, so CISC and so on, so that you get a more sort of general view. RISC isn't the only thing out there. Then in the last 6 lectures we'll explore system-on-chip design, giving a general overview of how system-on-chips are put together, and then look at multi-core processors over 2 lectures. We'll then look at graphics processing units in 2 lectures, and finally finish with future directions. Regarding recommended material, well, there's a recommended textbook by Patterson and Hennessy called Computer Organisation and Design, the Hardware Software Interface, RISC-V edition. So this uses the RISC-V processor architecture, the instruction set architecture that we're going to use extensively in this course. Patterson and Hennessy have actually written a number of different computer architecture books over the years. They're very good. Very often used for computer architecture courses. You'll find that there are older versions of their books in college libraries and so on. Some of the versions of the books are designed for more master's level and up. The book that I'm recommending is really quite suitable for this introductory course. Of course, there are a lot of other computer architecture books available as well, and some people find other texts useful. There's a great deal of material on the web as well. Some people quite like NAND to Tetris, and you might find that an interesting overview of sort of how to build your first computer. And finally, just note that this course actually has been called Computer Design for many years. So things like past exam papers and so on that appear on the departmental website will go by that older name. This year is the first year that we're starting to use computer design. Computers today have many form factors, and therefore there are many solutions. Of course, the general public might think about a computer in terms of, a device with a screen and a keyboard and so on. But of course we know that actually computers permeate our lives in so many different ways. Even something like a contactless bank card, people wouldn't think of that necessarily as a computer, but of course it's got a microprocessor in it, and that's got very stringent power requirements because it actually has to take the power from the radio field of the receiver. We've got things like hearing aids, which are actually quite complicated and very sophisticated computers that do an awful lot of audio signal processing. we've got the mobile phone. Of course, the mobile phone is just a phenomenal computing device these days. It's just remarkably powerful. Through to things like, a Cray supercomputer or a rack mount sort of PC server. And then we're starting to see things like autonomous vehicles. And of course, we all know about toys and washing machines and so on. The key thing is these all have different requirements. Something like a hearing aid has got very specific application, and so there can be an awful lot of optimization specifically for that device. Obviously, anything that's portable like a phone has got very stringent power requirements, and if you think about a mobile phone, actually the power drives so much of how that functions. So for instance, the power usage determines how big a battery you need, and then the size of the battery determines the form factor of the phone. These things are all interlinked and things that we need to think about when we're designing systems. And even if we think about the very high-end supercomputers, these days they do consume vast amounts of power, and there is ever demand to get efficiency there, and we've got ideas like power proportional compute, trying to make sure these very high-end devices really only draw the power needed to do the compute you need, which is actually quite a challenge. They tend to have a very significant base load before you even start doing any computing. If we look at a modern device like a mobile phone, it tends to consist of a large system on chip. In other words, this is a highly integrated chip with many functions in it, with some external memory that's quite often attached to that chip, which makes for a very small and power efficient design. It's quite surprising if you start looking inside such a system on chip, you'll discover there are things like large application cores. Here we've got ARM Cortex A57s and another variant of the ARM core called the Denver 2. But also we've got specialized devices like a graphics processing unit, a GPU, with various CUDA cores. We've got an audio processor, which is not too surprising for a mobile phone. And where we have other I/O devices, they often also have tiny processors inside them. And sometimes people are a bit surprised by this, but the thing is actually really low power tiny cores are so small you can sort of scatter them across the chip, and it doesn't actually use that much room, and it often allows for rapid design and also firmware upgrade in the field if there are any bugs. There's also a boot processor, and this is also something that sometimes surprises people. There's often a processor that comes up, there again a tiny little core that comes up when power's first applied, that does some power management, and it actually works through a boot sequence and actually boots up the big cores and boots up the whole chip. So take-home message from this is, on a modern system on chip on a mobile phone, you might think you've got 4 cores, but actually there are lots of other processors, and some of them are really weeny ones. All of these processors, however, really are what we call von Neumann processors. And one thing that may also surprise you is that the underpinnings of these processors is actually surprisingly old. So if we go back to 1945, John von Neumann, who's a mathematician, was actually involved in a project, EDVAC, which has actually principally been led by Eckhart and Maunchley. They were the engineers. Von Neumann, as part of this project, they had to produce a report on what they were doing to keep the sponsors happy, and von Neumann was tasked with drafting a report up, and this draft report has actually become quite famous because it really outlines many possibilities for designing computer systems, and it outlines the idea of a linear memory. So it starts off with the idea of having all the states sitting in a linear memory that's addressable. So what I mean by linear memory is, the addresses are just sequential integers for all the bytes or all the words in memory. And the processor actually, performs the programs and manipulates the data in memory. This also gives us the notion of control flow processors that execute instructions sequentially. And surprisingly, really, given all the advances in computer science, that this basic model pervades modern processor design, despite the fact it has a lot of limitations. And in particular, the bus or the interconnect between the processor and the memory is often referred to as the von Neumann bottleneck, and it's often the point where everything becomes sequential and it ultimately limits the performance of the systems. And whilst people have tried other exotic things like data flow machines, nothing else has really worked out well enough in practice, and it's never really gained traction within the field. But who knows, given the limitations of these processors, perhaps in the future we will see a shift to other things, and to some extent the shift to domain optimized processors like GPU is starting to shift us away, although you could say that GPUs are basically von Neumann machines, but that can just sort of work on multiple data at the time. More of that later. Even back in the 1940s, they identified that it was a real challenge to build a high-performance memory, and that challenge is still very much with us today. If anything, it's become even more tricky. So in one of these early reports they wrote, ideally one would desire an indefinitely large memory capacity such that any particular word would be immediately available. We're forced to recognise the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. And this is still very much with us today, and in fact, between the processor and DRAM, which is the commodity memory, we normally have various levels of caching, and cachers basically store recently used values or values that are likely to be needed again soon. We'll talk much more about memory hierarchy in a dedicated lecture later on. Today, memories and processors are all designed on silicon technology, and that technology has improved at a really truly remarkable rate. All the way back in 1965, Gordon Moore, who's founder of Intel, predicted that the transistor density on silicon would double every 18 to 24 months. This is often referred to as Moore's Law, although it's in many ways much more of a business prediction, and also looking at the sort of general technology trends. So we've seen the actual main feature size of transistors go from 10,000 nanometers all the way back in 1971 through today. We're actually seeing quite a lot of 7 nanometer chips, starting to see sort of 5 or 6, and in a few years' time we're going to see perhaps 3 nanometer chips. It's a remarkable rate of progress, and we've never really seen progress at this sort of rate in any other industry. Although I should note that this rate of progress is starting to slow up. There are just so many challenges. We're getting so close to, atomic dimensions and just challenges of manufacturability that things are really slowing up enormously. So you're going to see enormous changes within your career. And of course we wait to see if something replaces silicon, possibly something graphene based, although I'm skeptical. Here's an example from Intel trying to put Moore's Law into perspective. So let me just read this out to you. In 1978, a commercial flight between New York and Paris cost around $900 and took 7 hours. If you could have applied, the rate of improvement that we've seen from Moore's law to the airline industry, the way that we've seen it for semiconductors, then that flight would cost about a penny and take less than 1 second. It sounds a bit flippant, but actually that really is what's happened in the silicon industry, and it's hard to get your head around, to be honest, but it's what has really driven our subject forward at such a phenomenal rate, and also resulted in the sort of ubiquity of computers in our society, because back in the 1970s computers were big, large machines, and they were things bought by big institutions, large companies. They weren't the sort of thing that you just have in your pocket. So that change has been really very fundamental to our industry. So here's another quick example. The price per transistor on a chip has dropped to the level that actually the cost of one transistor is probably less than printing one letter in a newspaper. And when you think of what it does, what a transistor can do for you, that is just phenomenal. But of course it does mean that we can now have affordable billion transistor chips in your mobile phone. If we look at the costs in more detail over time, then we'll see on the left plot that the cost per square millimetre of chip has actually been slowly rising. However, of course, the number of transistors that we're getting on chip has been ever increasing. Okay, so the actual size of the transistors have been reducing, so therefore we get many more transistors per chip. Therefore, if we multiply these two factors together, we start to see that the cost per transistor has continued to fall, and it's fallen by orders of magnitude over time. However, the costs are starting to go up again, and actually we're starting to see a bifurcation in the industry. It used to be the case you always wanted the latest generation of silicon because the transistors were lower power, they were higher performance, and they were cheaper. Today, however, we're starting to see that the challenges of manufacture and just, as I said, reaching those physical limits mean that the latest generations of silicon transistors, the cost is starting to go up. And so we now have cheap processors which are slightly less dense, and more expensive silicon processors that are more expensive. And that seems to be set to continue. Let's dig into some of these costs in a bit more detail. First and foremost, yield is absolutely critical. Yield is the proportion of fully functional chips, and that yield number for a silicon process is a closely guarded secret because it really reveals the profitability of a silicon foundry. Many tricks are used to increase yield, including at design time, so it would add redundancy to memory arrays and so on. Also, yield is proportional to the chip area. Basically, the larger the chip, the more the transistors there are on it, and the greater the chance there is for a defect. Therefore, large chips get very, very expensive indeed. Of course, the converse is if you've got very tiny chips, they can be very inexpensive. And so this is one of the many reasons why a high-end server or desktop processor chip can be hundreds, if not thousands of pounds, and yet you can have very, very cheap chips in things like banking cards. We also have other non-recurrent, so one-off manufacturing costs when you're actually designing a chip, and they've generally gone up as the feature size has gone down. and critical to those is mask costs. So masks are used to basically, if you like, pattern the various layers on the chip in almost like a printing process. So the mask costs for something like a 10 nanometer chip are around $10 million per chip design. And you've got to offset that against the volume of chip sales. So one thing that's happened is that it really only makes sense to fabricate a chip if you're going to use it many times over. And actually you can see this perhaps more strongly in an industry, say like cameras. If you take something like Canon, they will have a signal processing chip to read information off the sensor and to do various bits of processing on it, and they will use precisely the same chip on their lowest end cameras and also their professional cameras. And maybe the professional cameras will have two of the chips in them, but it'll still be the same chip because they can't afford, they've got to sell the volume, and they just can't afford to do different chips for different market sectors or different market segments. The cost of the actual fabrication foundry, so this is where you go and make the chip, has also grown exponentially. So TSMC, so Taiwanese semiconductor manufacturing company, who make chips for all sorts of people, including Apple and so on. Their Fab 15 back in 2010 cost $9 billion, and their current estimate for a 3 nanometer fab is in the region of $20 billion. I mean, this is kind of ludicrous. You're getting up to the point where it's the gross national product of some tiny countries. These are huge investments, and the converse is you just think about the number of chips you've got to fabricate before you recoup that cost. The current indications are that the cost per transistor is starting to rise, as I mentioned in the previous slide, and so the semiconductor is bifurcating. We're seeing cheap chips and high performance chips. We're also seeing refinements to slightly older generations of silicon. So for example, at 45 nanometer there were lots of refinements at that process node, and it just kept getting better and better. And I think we're going to see this happen more in the future, that there will be some process nodes where the silicon foundry is set up and they want to keep churning out chips using that foundry and to drive the cost down. Moore's law has really pushed performance forward. Basically, smaller chips and smaller wires tend to result in a design, results in the gate going faster and pushes the gates closer together, and that reduces the amount of wire length, reduces capacitances, and everything gets better. At least that used to be the case. So we can see on this plot a whole range of processors over several decades, and then in the 1980s and 1990s we saw enormous performance improvements. Every new generation of silicon technology, every 18 months, would basically increase performance by around 52% a year. They started to slow down towards the mid to late 90s and into the 2000s, where we were seeing, around 20% performance improvement per year. But the clock frequencies were still going up and up. The turn of the millennium, things really started slowing up, and we were getting more density from Moore's law, but we weren't really starting to see the increases in clock frequency. We got more transistors to play with, so computer architects were trying to use those transistors to extract more parallelism to try and keep the performance up. But the actual clock frequencies were starting to plateau. And these days we really don't see much that runs beyond 4 gigahertz, and we're going to look in a minute at why that is. When people think about Moore's law, they're typically thinking about transistor performance, but actually wire performance is also absolutely critical. So let's look at how wires scale on chip and why actually we have a real problem today. So the resistance of a wire, and I've got a very simple wire depicted there in blue, the resistance is proportional to the length of the wire divided by the cross-sectional area, which is the width times the height. That wire has capacitance in relation to the substrate. So the substrate is where the transistors are, and the bottom of the substrate you can think of as being grounded. So that capacitance is proportional to the width of the wire multiplied by the length. Now, for those of you who remember some basic analog electronics, the charging time for a capacitance is proportional to the resistance times the capacitance. And if we just work through the maths, we suddenly see that the time constant for that wire is proportional to the length squared divided by the height. And if we think about this, every time we want to scale a wire down, to the next generation of silicon technology, we want to shrink the width and the height, because that wire shrinks in proportion to the transistor size. Actually, in order to try and keep this charge time good, wires have tended to get taller and taller, so they try and keep the wires as the H as big as possible. So you get sort of tall, skinny wires. But critically, if we think about the actual size of a chip, so how many millimeters it is on each side, that size has generally not changed enormously. A sort of cost-effective chip that's got reasonable yield, and if you've got some fairly high-performance processors on it, is of the order of 10 millimeters, and that distance hasn't really changed. However, we've kept wanting to shrink all these wires down, and in effect those wires have kept getting slower and slower, and they've certainly not been getting any faster. So if you want to go across chip, those wires are the same as they were 10 years ago. Okay. One thing we can do is to try and break these wires up. So if we halve the length of the wire, then each half segment goes 4 times faster. So actually that's quite interesting. We can then add buffering or repeaters along the length of the wire that sort of amplify the signal, and that is one way of actually trying to make long wires faster. And you can imagine there's a whole set of maths around optimal buffer insertion. But it is a major problem, and it does mean that we often can't get a signal from one side of the chip to the other side of the chip within one clock cycle. Now let's look at transistor scaling in a little bit more detail, and look at observations from a chap called Dennard back in 1974. So he observed that transistor dimensions are scaling by 30% on each side every technology generation, thus reducing the area by 50%, i.e. Moore's law. This reduces the delay through the gate by 30%, and therefore increases the operating frequency by about 40%. To keep the electric field of the transistors constant, the voltage has to be reduced by 30%, reducing energy by 65%, and power by about 50%. Therefore, in every technology generation, the transistor density doubles, the circuit becomes about 40% faster, and the power consumption, and this is of course with twice the number of transistors, stays the same. Okay, so that was why we were getting these amazing technology scalings in the 80s, 90s, and into the 2000s. In around 2006, this starts to break down. Critically, we cannot further decrease the supply voltage because when you decrease the supply voltage too far, the transistors actually start to leak too much, and you start getting what's called too much static power. In other words, even when the transistors are not switching, the static power, the power increases. Okay, and ideally we want to minimize static power and only have to deal with dynamic power, i.e. dealing with the power needed to switch the transistors. Also, the wires don't scale for the same chip area, and so the silicon technology no longer delivers on Moore's law for performance. So there's much more emphasis on computer architecture improvements to try and improve performance, because there's sort of a hunger in the industry to produce ever faster machines. And we're in this really tricky point now where actually the gains we can get from improvements to that classical von Neumann design has become incredibly challenging. And we're, if you like, seeing sort of the end of Moore's law and for performance, and the end of scaling for von Neumann machines. So it's a challenging time out there, but it does mean that it's a good time for computer architects to innovate. So one of the implications of Dennard scaling, or rather now the lack of Dennard scaling in modern silicon, means we're now in an era of what's called dark silicon. So let me explain this. While Moore's law is still just about delivering on transistor density improvements, we're not seeing a commensurate drop in power consumption per transistor. So the flip side to that is we have to proportionally reduce the number of transistors switching. In other words, for the next generation of chips, we may only be able to have the power budget to drive or to switch the same numbers of transistors every clock cycle as we did in the previous generation, even though we might now have twice as many transistors. And that's a bit of a head scratcher. So we're seeing a number of things happening here. One of the really obvious ones is a move towards accelerators, so domain optimized compute, which we only turn on when we need it. So a very good example of this are things like video codecs. So you've got a phone or a tablet will have a video decompressor like a H.264 video decompressor. And that's a dedicated piece of silicon that's been optimized just to do video compression, and therefore it's very power efficient. And we turn that on only when we need to do video decompression, and then typically, some of the processor cores and other bits of the chip will be put to sleep or put into a lower power mode to allow that video decompressor to run. And that does result in enormous power savings. We also see a move towards a range of processor cores, and sometimes referred to big versus little cores. So we'll have some very small efficient cores which are lighter loaded, and then we'll have larger cores for heavier workloads. And there you will see later on in this course that there's some really interesting trade-offs. If you want to get a really high performance core that tries to extract a lot of instruction level parallelism, you actually pay a lot of overhead for doing so. But sometimes this is what you need. You've got some sequential software and you just want to run it faster. On the other hand, if you can actually map things onto smaller, much more efficient cores, you can actually have big power savings. And so, on modern mobile phone and tablet chips, they often make these trade-offs. And finally, of course, there's a simple idea of race to dark. So, we turn processors on, we do all the work that we need to do in some period of time, and then we aim to basically turn the device off. Or if it's something like an accelerator, we only turn the accelerator on when we need it, and we power it off when we don't need it. Another control knob we have is the voltage that the device is running at. The actual active power of the device is proportional to the capacitance, and that's basically proportional to the silicon area and thus the feature size, multiplied by the voltage squared. Okay, and that square, of course, is very important. If we make a small decrease in voltage, we're going to make a big decrease in activation power. The other factor is the clock frequency. And finally, the activity factor, or the proportion of transistors switching, which is, of course, linked with dark silicon that we've just talked about. So, obviously with dark silicon, the idea is that we reduce the activity factor. And then if we actually look at the performance, so over a limited range of voltage, we actually get a sort of we can get into a linear range where the frequency that the circuit will operate at is proportional to the voltage. And that's very interesting. So for a limited range of voltage, if we reduce the voltage just a little bit, the performance will drop off a little bit, but actually will make some really big power savings. The flip side is that if we push the voltage up, we can increase the clock frequency, we can make it go faster, but actually we're going to consume an awful lot more power. And there's a really interesting trade-off there, particularly as CMOS circuits get slower as they get hotter. Okay, so we push the voltage up, the device will work faster, but then it's going to start getting hotter, and then it will stop operating correctly unless we start reducing the voltage. So we have this notion of dynamic voltage frequency scaling, DVFS is what we call it in the industry, where we adjust the voltage with frequency to perform that trade-off. And the DVFS is often marketed as things like Turbo Boost or Power Now and other crazy names. Of course, this also links in with the whole idea of overclocking, which, if you've got a gaming rig, you might want to aggressively cool the system. Now, of course, modern chips will actually do this dynamic voltage frequency scaling. So if you just do aggressive cooling, then actually the chip will effectively do overclocking all by itself. It will dynamically adjust the frequency and give you better performance. Sometimes the BIOS might allow you to tweak frequencies, but these days, as I said, it's such a subtle balance of voltage, frequency and temperature that really you need to rely on the sort of built-in settings that the manufacturers provide to optimize it. Still, aggressive cooling will make your device go faster because it can operate at a higher frequency for longer. And the final note is, operating the frequency of a chip beyond its manufactured recommendations will start hitting reliability. And it's actually quite complicated how you work that out, when you're going to see reliability problems. So, yes, basically beware if you want to get into overclocking. A perception that people often have is that if a computer is idle, then it ends up in a very low power state. And I'm afraid this often isn't the case. So here I've just got some numbers for a particular Intel i7 processor. At 100% load, this particular processor was running at 258 watts. At 50% load, it was running at 170 watts, so 66% of the power. And at only 10% load, the power's come down a bit. It's down to 121 watts, but that's still, only just slightly less than half the power of running it at full load. It's quite interesting to compare that against something like a Raspberry Pi 4, which has some ARM RISC processors on it that are designed with power efficiency in mind. So, the Raspberry Pi 4 is using a fraction of the power, but is definitely much more than 10% of the performance. So that's interesting, and that's one reason why things like mobile phones have ARM processors in them that are highly power efficient, and desktop machines that need to run legacy x86 software tend to run these complex instruction set processors like the Intel i7. It's also interesting to think about, to what extent things are active in data centers. So numbers I've seen for things like Google data centers, they tend to operate in the 10 to 50% load range, and at 100% load, less than 1% of the time. So this really motivates the idea of energy proportional compute, and the industry really needs to work harder and is motivated to do so, to try and ensure that the amount of energy consumed is proportional to the amount of compute being done. Static power makes this challenging. As I talked about dynamic voltage frequency scaling, if we drop the voltage too far, the static power starts to increase. The flip side as well is that transistors with lower static power tend to be slower. And I'm not going to get into the semiconductor details of why that's the case, but it is, I'm afraid, the case that you can make various choices, and in fact you can even choose 2 or 3 different sorts of transistor when you're laying out a chip, so that you can have some slower transistors that have a lower static power, and a few higher performance transistors that have higher static power, to try and make that trade-off at design time. Moore's law for silicon transistor density improvements, of course, not only applies to processor chips, but also it actually applies reasonably well to DRAM, which is volatile memory, and non-volatile memory like flash memories. Interestingly though, there's similar sort of improvements we've seen for storage. So magnetic hard disks have actually improved at a greater rate than Moore's law, which is really staggering. So the actual density of bits on that magnetic storage platter. Nevertheless, despite the amazing improvements we've seen in hard disks, the actual power efficiency and low latency access time is really driving us towards solid state storage to get that performance and power efficiency. We're also seeing changes from legacy interfaces for these devices like SATA, which are very much focused on magnetic disks, now to NVMe based storage, which uses basically a PCI Express interface, and you get much more of a memory-like interface rather than a block disk-based storage interface. Critically on NVMe, you get a lot of parallelism, so you can issue an awful lot of requests and sort of stream data in and out of the system very efficiently. Nevertheless, spinning magnetic disk is still very cost-effective for long-term storage. And so we still see sort of hybrid systems, and of course the industry is looking at other storage systems as well for what they call, often referred to as cold storage, which is where you want to store data, particularly in data centers, that might not get used again for a long time and certainly won't get modified. But still you want to be able to store it efficiently, and at the moment a lot of that cold storage is on spinning magnetic disks that can get powered off, so they use racks of disks and only turn a certain number of them on at any one time. You can also apply Moore's law to some extent to networking, because the improvements in the silicon technology improve the switching speed of the transistors, and that in turn determines the bandwidth we can get over copper or optical links. There are also other factors. Of course, the speed of light is going to limit the actual latency of communication, how long it takes to get bits from one place to another. Nevertheless, as we can see from the table, there have been a lot of improvements to bandwidth. So here I'm just looking at when standardization has come out. So 10 megabit Ethernet was standardised in 1990. Of course, these days we routinely use gigabit networks. That was actually standardised in 99. 10 gig networking was standardised in 2006. And these days we're starting to see 10 gig network interfaces on higher end desktop machines and server machines. And 40 gig and 100 gig Ethernet are coming along. Once you get these higher data rates like 40 gig and 100 gigabit, it actually becomes very difficult for a processor to either produce or consume that traffic, because obviously the processors aren't actually getting any faster. So that's an interesting challenge. With ever more transistors, we obviously have a design and a verification challenge. Does design get exponentially more difficult as we have exponentially more transistors? And do we need exponentially bigger design teams, or are there efficiencies to be had? Well, there are a number of solutions, and in fact we've seen the same sort of thing also happen in the software space, where people build ever more complex applications, and yet we don't have bigger and bigger software teams. So we do hierarchical decomposition, we do replication of components. So there were standard libraries now of processor cores and memory blocks and so on, and that's kind of interesting. If you think way back when, in very early days of designing circuits, your library would be things like logic gates, and you'd be stitching together logic gates. And these days we actually have high-level processors and memory blocks. These really complicated blocks that we can place down on the chip, and they're then decomposed into other libraries of lower-level components like flip-flops and gates and so on. We also rely a lot on well-specified abstract interfaces, so standardized bus memory or switched interconnect like AMBER or AXI. And increasingly, in fact, now the industry routinely uses hardware description languages, and they're starting to use slightly higher level hardware description languages. So system verilogs that you're going to use in the ECAD and architecture labs is relatively low level, but exceedingly widely used by industry. And for research purposes in the department and in other places, we use BlueSpec System Verilog, which is only slightly looks like System Verilog. It also has influences from functional languages like Haskell. In fact, it's written in Haskell. So to conclude, we're still using von Neumann style processors. I mean, this is an idea from the 1940s, for crying out loud. Surely we can do better. And it's really not an efficient general purpose processor, and I've heard some people refer to it as the Turing tax. Do we want to keep paying the Turing tax? As we've seen, accelerators help a bit, but we still very much have von Neumann processors, coordinating everything. And that's a way to go, but surely we can do better. Even if we map algorithms directly to field programmable gate arrays that you will also be using in the ECAD labs, we get much more efficient, much more power efficient mapping of an algorithm to a circuit, even though FPGAs are typically around 15 times slower per gate. The golden age of silicon technology improvement is over. So Moore's law is still delivering on transistor density for a little bit longer, though we don't quite know how much longer. And I think practicalities in manufacturing are really going to impact how far we can go. And we've seen that Dennard scaling, or the lack of Dennard scaling, means that our chips are just not getting any faster, or certainly not by much. So there's ever more need for better computer architectures. And finally, computer systems are now power limited. We have a lot of mobile devices, and that's very obvious. But actually, servers around the world and other computer systems use a vast amount of electricity. And at the moment, it's estimated that something of the order of 3.5% of all global emissions come from computers, and this could easily rise to 20%. This just isn't sustainable. That said, there is a sort of flip side that actually using computers can potentially minimise power consumption and minimise emissions. We've already seen for the internal combustion engine that actually computer-controlled engines have reduced emissions enormously. We can also, of course, use computers to minimise the amount of travel we do. And it's been interesting during COVID to see just how much can be done in virtual space. So there are a lot of challenges. It's an exciting time. Things are moving forward, and I hope you will enjoy this course. And I'm hoping you will also think of innovative things that could be done to improve computers of the future. And with that, I'd like to close.